Hello chemists, welcome to Preliminary Chemistry and the water topic, video number 6 on intermolecular forces. I want to have a quick review of intermolecular forces because I know it's causing a few little problems and I think it's worth just visiting some of these key concepts. So far we've looked at the fact that there are two main types of forces that hold atoms together, and those two types of forces are chemical bonds and physical bonds. Chemical bonds come in three types: ionic, covalent, and also metallic. Network structures or arrays like ionic salts, covalent networks like diamond, only contain chemical bonds, and so therefore they tend to have very high melting and boiling points. They tend to be quite rigid in terms of their solid structure because of those the lack of weakness between any of those bonds. Of course, there is a possibility of shattering for some of these ionic substances. For example, if you can push the structure out just slightly, so where instead of positive ions lining up against negative ions, you push positives and positives together, they will repel each other and cause some shattering. But certainly in terms of trying to break the bonds down into a molten mass or into a gas, much more difficult when substances only contain chemical bonds. These bonds are fairly strong bonds, and that accounts for those high melting and boiling points. Because these are occurring within the molecule or within the structure, we call them intramolecular, within the molecule. Now, of course, we need to be careful that we don't use the term molecule to refer to an ionic substance. Really, the formulas we write for our ionic substances are empirical formulas, not molecular ones. The covalent ones tend to be the ones that are more dominated by molecular formulas and referred to as molecules. Nonetheless, when we look at our covalent substances, we find that there are intermolecular forces, which are the ones between the molecules. And these are the ones that are the subject of this particular video. Again, there are three types that we need to look at. Generally speaking, these are weaker forces of attraction and therefore are more easily broken by things like the addition of heat. The three main types are hydrogen bonds, dipole-dipole forces, and dispersion forces. Now, you may see some reference in different textbooks to van der Waals forces, or even sometimes to London forces. We're going to use the term dispersion forces, and that's the only one that I'll expect you to be familiar with. Now, hydrogen bonding was something that we looked at when we were looking at the polarity of water molecules. So let's look at the more general case of a dipole-dipole interaction. Now, dipole-dipole interactions have to occur between molecules in which the bonds themselves are polar. Polarity is the result of permanent dipoles. So something like hydrogen chloride forms a dipole. There is here a covalent bond, but the two electrons in that covalent bond are held more closely to the chlorine than they are to the hydrogen. And as a consequence of that, this becomes a polar bond. This polar bond has a slightly negative region around the chlorine and a slightly positive region around the hydrogen. When another hydrogen chloride molecule comes near, the opposites attract, and we get bonding occurring. Because this is a dipole, and this is a dipole, the interaction between the two is called a dipole-dipole interaction, and hence this term. Now, one of the important things that we want to just remind ourselves is that the fact that we've looked at hydrogen bonding, which this is another example of, hydrogen bonding is a subset of the dipole-dipole interaction. And it must involve hydrogen, involving hydrogen, obviously, hence the name, and the hydrogen must bond with oxygen, nitrogen, chlorine, or fluorine, one of the very strongly electronegative atoms. And this is because it's the only way to make sure that we have that really strong dipole-dipole interaction. But these are not the only substances that can form dipoles. The important thing to remember about dipoles, and really about any of these intermolecular forces, is the fact that they are based on electrostatic attraction. That is, the interaction between a positive charge and a negative charge. These two will attract one another. The more strong the charge, the higher the charge, the more strong the force, and the smaller the distance, the larger the force as well. And that's an example of the inverse square law. The electrostatic interaction is what draws the oppositely charged poles closer together. And the dipole-dipole interaction is what causes an increase in relative melting and boiling points for similar molecular weight substances, because dipole-dipole are relatively strong forces. The interaction between these two is quite strong, and therefore you need a reasonable amount of energy input to push these apart from one another. By contrast, dispersion forces are the weakest of the intermolecular forces. We know that there are certain covalent substances that can exist as solids and liquids at room temperature. Iodine can exist as a solid and bromine as a liquid at room temperature. But a large number of these are gases at room temperature. These substances themselves, iodine and bromine, are held together in the solid or the liquid state by something different, not ionic or polar covalent interactions, but by something else, a dispersion force, the weakest type of force that nevertheless still holds these particles together. The main thing to remember about the difference between a dipole-dipole interaction and a dispersion force is the fact that the polarity that causes the force of attraction is temporary for substances that display these dispersion forces. It's permanent for the substances that display dipole-dipole interactions. So the induced polarity is a result of the electrons in motion. Now this is always the case, but in terms of the amount of time in which the paired electrons in the bond, the covalent bond, spend between each atom are roughly equal for substances in which we see dispersion forces, but unequal in substances which display dipole-dipole interactions. And this is the result of this permanent polarity. Think of it this way: at any given time, the shared electrons may be closer to one atom than the other. And as the electrons move closer to one atom, if this is the atom, then what they do is they will push electrons away from the other atom. So the effect of this is, if we have, say, iodine, and iodine, and another iodine and iodine, if the electrons are hanging around this one here, then the extra electrons will be pushed away, making this a slight negative and this a slight positive, and then the force between these two then becomes our dispersion force. Molecules will have an induced polarity due to that temporary dipole or charge separation. So as the electrons are cycling between the two atoms, atom 1 and atom 2, the polarity is constantly changing from, let's say, a negative and a positive, and then in the next instant, a positive and a negative. The charges are always going to be opposite, and this induced dipole is going to interact with other molecules that are adjacent in the nearby area. So these dispersion forces are the result of the temporary dipole-dipole interactions. So they are still a dipole-dipole interaction, but they're a temporary one. And it's very important, if you use the term dipole-dipole interactions in your explanation of dispersion forces, that you make sure you use this term, temporary interaction, temporary dipole-dipole, or temporary polarity, because there's no consistency for these dispersion forces in terms of which atom is going to be more negative or positive. Dispersion forces are generally weaker than those induced by polar bonding, and so therefore weaker than dipole-dipole interactions. However, one of the important things to remember is that if we have very large molecules, then they can also display a relatively high melting or boiling point, simply as a consequence of the fact that there are a larger number of dispersion forces per molecule than their smaller cousins. So that's one of the reasons why we find, for example, in the sequence of alkanes, an increase in melting point as we increase the number of carbons. Put simply, as the relative molecular weight increases, so does the melting point and the boiling point. This is a result of an increase in the attractive strength of the dispersion forces between the molecules. So where we have something as simple as methane attracting another methane, the number of dispersion forces between these two molecules will be much less than, say, butane. And that's simply because the larger molecule has more options of forming dispersion forces between these two. And hence there will be more of them to break in order to move the molecules apart from one another. This is also an effect which has been observed in polymers, and it's going to be very important when we look particularly at things like polyethylene in our HSC course. And the other thing, I guess, to look at before we leave this particular video is dispersion forces are also the forces which hold the noble gases, the monatomic molecules, in the liquid state. So helium, for example, exists as a monatomic molecule, and it's held to another helium by a dispersion force. Thanks for watching.